All right, hello and welcome back. So this is another requested video. So this ALEKS topic is called Predicting Color and Magnetic Properties from a Crystal Field Theory Energy Diagram. This is a cool little topic. It's fairly straightforward once you understand all the different steps. But again, like all of these things, it's like the things that we're actually doing are very straightforward, but knowing what to do, that's really the key, right? So let's go ahead and start breaking this one down. I'm going to do two different examples of this topic. The first one, obviously, I'll go into a little bit more depth, and the second one we'll move through a little bit more quickly. So the first thing that I've done for this question, this instance, is sort of underline some of the relevant information. So we're told that it's a certain strong field ligand. So, the strong field ligand, what that is telling me is that this distance here, this delta between our lower energy level d orbitals and the higher energy level d orbitals is bigger, right? So strong field means that delta is going to be larger, and that indicates this is very likely going to be a low spin complex. So the fact that it's a strong field ligand, this is essentially saying low spin complex. And that is an important piece of information. We really need to understand why we're saying that, why we're drawing that conclusion, because that's going to affect how we're going to fill in the electrons in our box diagram, and that's also going to affect our answers that we're putting in. So that's a really important thing to note and to make sure you understand. The fact that it says octahedral is not super relevant. We're given the box diagram here, so that's relevant for filling in our electrons, but since they've filled in this box diagram already for us, it's just sort of nice to reiterate, I guess, that this is a splitting that we would see for an octahedral complex. Mn3+, so I've already written out the electron configuration for manganese 3+, and again, you should be able to do this by this point in time. We're looking for where manganese is. We can count the d electrons. Since it's a 3+ cation, we know that there's going to be some 4s electrons that are in the neutral complex, the neutral metal, but since it's 3+, we're going to lose those 4s electrons first. We're also going to lose a d electron to get to this electron configuration here. So again, the electron configuration is really important because we need to know how many electrons we need to fill in our diagram. So this is sort of the first pieces of information. Number one, you need to determine, is it low spin or is it high spin? Number two, you need to figure out what the electron configuration is, and so you know how many d electrons you need to fill into your diagram. So then step three is really just to fill in those electrons. So I've got 4 electrons that I need to fill in. I know that this is a low spin complex, so I'm going to go 1, 2, 3. That's pretty straightforward, right? That's going to be the obvious first 3 electrons. And then the 4th electron, that's where we really need to pay attention. In terms of, does it go up here? Is it a high spin complex, or does it go down here? It's a low spin complex. And I just want to reiterate one more time about sort of the significance here, what's going on with this last electron. Because the delta here is large, it makes more sense for this electron to pair. There's a certain pairing energy that the electron has to sort of pay, essentially, to go into this XY orbital and pair up with this other electron. And if that pairing energy is lower than the energy that it takes to go up to this higher energy level, then we're going to see this low spin complex. If that pairing energy is higher, if this is a weak field ligand, where the energy level is energy difference between this is much shorter or much smaller, then it makes more sense for that last 4th electron to go to the higher energy level, as opposed to paying that sort of pairing fee to join up with this other electron here. So just want to make sure that that's clear. Now we can start answering our questions, or at least the first 2 of these questions. So how many unpaired d electrons? So we've got 2 here. We're just counting 1, 2. And of course, if you made a mistake on if this was high spin or low spin, you're going to be, in trouble already. But that's why that's important. Is the complex paramagnetic or diamagnetic? So the definition here, paramagnetic, means that there's unpaired electrons. It's different people have different ways to remember paramagnetic versus diamagnetic. The way that I always remembered it is that di means 2. 2 means that they're all paired. I know it's a little bit confusing because it says paramagnetic. You might think, well, that means paired, but whatever you need to do to remember that paramagnetic means unpaired electrons, and diamagnetic means that all the electrons would be paired in a diamagnetic complex. So then now predict the color of the complex. So this is going to take a little bit longer to sort of lay out and explain, but basically what is going on here is these electrons down here can absorb a photon of light, and when they absorb a photon of light, then they can jump up to a higher energy level, right? So these electrons down here, if a photon comes in, bashes into that electron can jump up to a higher energy level. So if you've studied, the electromagnetic spectrum, you've worked with, some of these Planck's constant type equations and stuff like that, this concept will be familiar to you. But this is really how, how complexes are colored by these movements of electrons between, in this case, d orbitals. In organic molecule cases, it could be, like a pi orbital system or something like that. But in this case, this electron is going to be absorbing a photon of light, jumping up to a higher energy level, and then, by various means, relaxing back down to this ground state electron configuration. So this photon of light that's coming in, that's going to be very relevant for, do we observe a color in our complex? So there's a number of equations that will sort of govern this behavior. So E equals Planck's constant times frequency. That might be an equation that looks familiar to you. That's a sort of a common equation that we've used for dealing with photons. And then another equation that might be familiar to you would be that the speed of light, c, is equal to the wavelength of light times the frequency. So these two equations you've probably dealt with or used in a number of different ways. We can combine these two equations and sort of rearrange things to rewrite, basically solve for the wavelength of light in terms of these other things essentially, and get rid of the frequency. We don't have any frequency information in this problem, and we can sort of solve for one and get rid of it. And if I do that and I rearrange all of this, I'm not going to do that algebra, but wavelength of light can be rewritten in terms of these other equations as Planck's constant times the speed of light divided by the photon energy. So this equation here, this is really going to be the key for figuring out this last part. We really need to know what the wavelength of light that this photon, so this photon is going to have some energy associated with it, that photon has some energy associated with it and also a wavelength associated with it that's going to be sort of determined by this equation that we've derived here. And when that wavelength of light comes in and interacts with this complex, that wavelength of light is going to be absorbed. It's going to be taken out of the visible spectrum. And that's a very important thing. And we'll talk a little bit more about that once we sort of get there. But that's the take-home concept. So let's go ahead and sort of fill in some pieces here. In this equation, we're going to be solving for the wavelength. That's what we're looking for. Planck's constant is a constant, so we know what the value of that is. It's 6.626 times 10 to the minus 34th. I'm going to put in the units here. So joules times seconds is the units for Planck's constant. Speed of light, I've always just used 3.00 times 10 to the 8th meters per second, so seconds to the minus 1. I think in ALEKS they use like 2.9979 or something like that. I've always just used 3. It works just fine. E is going to be the energy of one photon, and that's a really important aspect. So in this equation here, this is the energy of one photon, and the Planck's constant for one photon, and the frequency for that one photon. So when we're dealing with these equations, we really have to specify what energy sort of we're talking about, and then the units for that would be joules, of course, right? Since we've got joules in our Planck's constant, so I'm going to put joules right there. So to solve for the wavelength of light that this electron is going to absorb, we really just need to apply this equation, but we need to figure out first what the energy of that photon is going to be. And if you remember, sort of if we think about like conservation of energy, the distance that this electron is going to jump up is going to be equal to the energy of the photon that it's absorbing. So we can actually see we've got this energy level at minus 650, this energy level at minus 375. So we can actually calculate what the distance, what the energy is in kilojoules per mole between these lower energy d orbitals and these higher energy d orbitals just based off of the difference between this number 650 and 375. So that's going to be a difference of 275 kilojoules, right? So to go from here up to here is 275 kilojoules. So the energy, we'll just sort of work this out. I'm going to write energy equals question mark. So 275 kilojoules per mole. We've got to be really careful with all of our units here, right? So we're going from minus 650 up to minus 375. That's 275 kilojoules per mole. And I want to convert that into joules for one photon. That's really sort of the thing that we're looking for here, is I need to have the energy of that one photon that's coming in to interact with this electron to jump up to the higher energy level. I know that, if this electron gains that amount of energy to jump up to this energy level, that amount of energy would have been absorbed, right, from the photon. So that's where we're getting this information. So let's just do some dimensional analysis. I'm going to convert this first to joules. So I know that for every 1 kilojoule, that's 1,000 joules. So my units of kilojoules will cancel out. And then I want to get rid of this mole essentially. So I'm going to say times 1 mole is Avogadro's number, 6.022 times 10 to the 23rd photons. So this is just basically converting, well, if I've got a mole of photons, this is the amount of energy, but I just want to know for just 1 photon how much energy that's going to be. I can get rid of those, and then we'll be left with units of joules per photons, which is what we want. So let's go ahead and calculate this. This is going to equal 4.567 times 10 to the minus 19th joules per photon. So that's just sort of doing this calculation here to get to this energy, and that is our E that we can then plug into our equation up here. So let's go ahead and do that. So our wavelength for this photon that's going to be coming in and being absorbed is going to equal Planck's constant, 6.626 times 10 to the minus 34th, times the speed of light, 3.00 times 10 to the 8th, divided by the energy of that one photon, 4.567 times 10 to the minus 19th. And then we can see that our units are consistent here, joules, seconds, meters. So that's going to be telling us that this wavelength that we're going to calculate is going to be in terms of meters. And here we've got joules per photon, so that'll make sense. And we get an answer of 4.35 times 10 to the minus 7th meters. So that's, again, very important. So now we basically just need to convert this from meters into nanometers. So we'll do that right down here. 4.35 times 10 to the minus 7th meters times 1 times 10 to the 9th nanometers. This is just the conversion factor for meters to nanometers, equals 435 nanometers. So the significance of this is that that is going to be the wavelength of light that's coming in and being absorbed by this electron, or any of these electrons really, to jump up to this higher energy level. So if we think about the electromagnetic spectrum, and we've got somewhere in here, here it is, this little diagram, each of our different colors of light has a different wavelength associated with it, right? So if we remember back to your electromagnetic spectrum, and we have that normally, it's written out, basically what we're saying is that a certain wavelength of light is going to be removed from that spectrum. So if I'm removing wavelength of light that's violet, essentially between 400 and 450 nanometers, 435 right here, something like that, if I'm removing that light, then the opposite side of this color wheel, that's going to be the color that we observe. So it's a little bit confusing there, I think, sort of how we get to that final answer of this is going to be yellow or orange. We're saying that it's going to be yellow or orange because we're removing the opposite color from the color spectrum. So if you think about white light has all of these colors together, all of these wavelengths of light together. And if you remove one part of that, then the opposite color is going to be more dominant. We're going to see more of that. The complex is going to appear to be orange or yellow because that's the light that's sort of remaining after we've removed some of this 435 nanometer light. So we're removing the opposite color of what the complex will actually look like. So this is going to end up being orange or yellow. And again, I'm getting that because we've got 435 nanometers down here, and that light is going to be right here, 435 nanometers, opposite color, orange or yellow. Okay, let's do one more. I'm gonna, again, like I said, run through this second one a little bit more quickly, skip a few steps, but hopefully that first part will be clear so you can follow along. So here we're told it's a weak field ligand. So if it says weak field ligand, then I'm gonna say high spin. Right, so weak field indicates that this distance will be a little bit smaller, and then that our electrons are going to be higher spin. They're going to be able to jump up. That's going to be more favorable than pairing up. Cobalt 2 plus cation. So if I've got cobalt 2 plus cation, then our electron configuration is going to be, where's cobalt? Argon 3d7. Yep. So argon 3d7 is going to be the electron configuration. So we're going to have 7d electrons. We're already told that it's octahedral. So we can go ahead and fill in our electron configuration diagram here. So 1, 2, 3. Now we need to decide where our next electrons are going to go, right? Because it's high spin, I'm going to start going up here. 4, 5. Now we're going to drop back down for the last 2, 6, 7. So that's how you would sort of fill this in. And again, if you chose low spin, you would be filling in this diagram differently, right? If you chose low spin, you would fill this up, then you would have 1 up here. So you would have a different number of unpaired electrons, and you would get the sort of first part wrong, right? So this is really important, determining is it high spin or low spin based off of what we're told about the ligand field strength. If it's weak field, that means high spin. If it's strong field, that means it's low spin. Okay, so number of unpaired electrons is 3. Obviously, this is going to be paramagnetic. We've got unpaired electrons. And then the distance here is going to be 225 kilojoules per mole, right? So going back to our wavelength is going to be equal to Planck's constant times c over the energy. We know that our energy is going to be equal to 225 kilojoules per mole. And then we can take that information and basically convert that, right, like we did before, times 1,000 joules over 1 kilojoule times 1 mole over 6.022 times 10 to the 23rd photons. That's going to be the calculation that we're going to use to figure out what this energy is going to be. We can then plug everything in. Basically, I'm going to skip those steps for now because this video is getting a little bit long. Times, just sort of calculate all this, and you should end up with 5.32 times 10 to the minus 7th meters, which is equal to 532 nanometers. So again, I skipped some steps there, but we're just plugging in Planck's constant like we did before in the earlier part of this video. Same with the speed of light. For E, we're doing the same calculation where we know that the distance here for that photon that's coming in, I like sort of drawing it. That's supposed to be a sine wave. It's very close, right? Then that's going to promote this electron up to the higher energy level. So the energy of this transition is going to be equal to the energy of the photon. We can calculate that this way, and then use that to plug into this equation to solve for the wavelength of light. Once we have our wavelength of light, we're going to go back to our color wheel. So 532 nanometers would be somewhere in here, would be somewhere in the green area. So again, what that represents is that the green light is being removed, it's being absorbed by that photon. So then the opposite color, red/orange, so if we're absorbing 332, so like right here, more like red, if we're absorbing the green light, then the complex would be more predominantly red. So then we would choose red or violet. So that's basically how you do it. I do want to mention one last thing for this white or transparent. The way that you would run into that is if you had a full D10 full orbital or full electron configuration diagram, because there would be no way for these electrons to be promoted to the higher energy level. I guess another way to put it is that if these higher energy orbitals are full, there's no space for an electron to get promoted into that orbital, right? So if this was full, if you had a high spin complex and these were full, then you're not going to be able to promote, I guess it could be low spin too, but you're not going to be able to promote electrons up into these orbitals if they're already full. Then we're not going to absorb any light, and that's going to be white or transparent. Really, I sort of prefer colorless, but that's fine. White or transparent or colorless. All right, hopefully that's helpful. And again, thank you for the request.